Math 265A, Cuesta College. I'm Joe Vasta, and this is 4.6 Linear Approximations and Differentials. And your homework looks like this, the first part of your homework. If you actually read the book, this is going to look more complicated than it really is. So just pay attention to this lecture, and we'll see that linear approximations are something you already know how to do. In differentials, it's a little different, but we'll get through this. Write the equation of the line that represents the linear approximation of the following function at a given point A. And then we'll use the linear approximation to estimate the given quantity. So on that part right here, this part is part B. So that's part B right there. Okay, what are they asking you to do in part A? What they're asking you to do is they're really asking you to find the equation of the tangent line of this graph at the x value of 3, and they call it A. So how do you find the tangent line? Well, you actually need a point and a slope. The point is going to be 3, and the y value is gotten by going f of 3, which is 3 squared, which is 9. So we're trying to find a line that has the point 3, 9 and a slope. Now how do we get the slope? We take the derivative. The derivative is the slope function. So f prime is 2x, and the slope at this point, we put 3 in for x. We get 2 times 3, which is 6. So 6 is the slope. So what they want us to do is they want us to find the line that has this point and this slope. So lines look like this. Y equals mx plus b. And we have y equals m, which is 6x plus b. So what we're trying to find now is b, the y-intercept, by plugging 3, 9 into this equation. Okay, so we'll bring it up here. We end up getting 9 equals 6 times 3 plus b. 9 equals 18 plus b. b equals -9, or -9 equals b. So now we know what b is. We already know what m is. And our line looks like this. Y equals 6x minus 9. That is the linear approximation. So why are they changing words on us? We're going to see in part B. The first thing we want to do is, this is just a tradition of what people do with this, is they write this as a function. You know, a linear approximation is a line, so they're going to replace the y with L of x. L of x equals 6x minus 9. That is the answer for part A. And that's pretty much what they want you to do. Now, the book is going to make this more confusing, and I'm going to get into that. You're like, oh, you want to show us how to make this more confusing? Yes, I will. But before we do that, let's just see graphically what we just did. Graphically, we have this parabola here. It's kind of in gray. And then here's the point 3, 9. And then here's the tangent line at the point 3, 9. And so we've seen this before, except now what we're doing in this section is we're calling that tangent line L, function L, and then our original function is function F. And somehow we're saying this is a linear approximation. So let's get back to this. And this is called a linear, I'll abbreviate approximation. Approximation of f at 3. Okay. And all it is sometimes people will call this the tangent line approximation of f at 3, and some books will call this the linearization of f at 3. So depending on which calculus book you use, our calculus book calls it the linear approximation of f at 3. Now, why is this the case? Why would we go through this and make a big deal out of this? Because of things like Part B. So Part B says, use the linear approximation to estimate the given quantity. The given quantity is f of 3.1. Okay, so Part B, they want us not to go f of 3.1, they want us to go L of 3.1. Now, it's not so obvious in this example because I wanted to make the example simple, but it is a lot easier sticking values into a line than it is sticking values into something that's nonlinear, and things can be uglier than x squared. And so when we put this into the line, we're really just going, we're using this right here, 6 times 3.1 minus 9, which you can use your calculator on that, you end up getting 9.6. Okay, so that pretty much finishes this problem. And you're saying, well, what did we just do? Well, we could have, in our calculator for this problem, we could have put 3.1 into the actual function. So this is just FYI, you don't have to do this in your homework. F of 3.1 happens to be 3.1 squared, because f is x squared, and if you do that on your calculator, or you can do that by hand, you end up getting 9.61. So 9.61 happens to be a pretty good 9.61 is the exact answer. This is what we wanted. We approximated it by using the tangent line, and those are pretty close. That's what I was trying to say. And let's just go ahead and see what that looks like on the picture. It's actually hard to see on the picture because 3.1 is like right here. So f of 3.1 happens to be this gray line. They almost look the same here, and the gray line will give you a height or a y value of 9.61, whereas the line L, that red line, gives you a height of 9.6. But we took a value that was really close to 3, like 3.1, and these guys are going to be almost the same. Now, if I took a point that was further away from 3, like 2 or 1, then those altitudes or those y values of both of those graphs are not going to be close together. And so this is why it's called the linear approximation. So let me kind of summarize what I just said there. We have these two graphs, F and L now, and we could say this. We could say that F of x is approximately equal to L of x near the x value of 3. Okay? And so sometimes in the real world you'll have this really ugly function, and you'll have to evaluate lots of points, maybe hundreds or thousands of points right next to an x value of 3. Maybe you're doing some application for either cryptography or whatever, and instead of having the computer crank f of 3 for something that's worse than x squared, we find the linear approximation, and then we can do those 1,000 calculations very simply using a line. So that is the application. And right now, I remember when I first saw this in calculus, I kind of hated it, and also because I think my calculus teacher, maybe they said it, but I don't remember them emphasizing that the linear approximation is just a tangent line, something we already know how to do. Okay, so we are done with the problem. We were done with the problem right when we got this. I'm going to do something a little crazier. So, you know, some of you might want to just skip ahead on this. I'm going to look at L of 2 and F of 2 for this example. And I'm writing it in red. This is not part of the problem. And if you put 2 into here, you end up getting 6 times 2, which is 12. 12 minus 9 is 3. You put 2 into F, which is x squared. I want to see if we're still capturing that. Yeah, we are. You'll get 2 squared, which is 4. Now, would you say that 3 and 4 are close? No, they're not. They are kind of close, but they're not as close as these values here. And it was because we picked 2. And so, you know, when picking x equals 2, we are not, and I'll put this in quotes, near 3 on the x-axis. Now, maybe I should have done something more extreme and picked the point like x equals 100, and then you would have seen a really big difference. Now, in terms of the graph, L of 2 happens to be 3, which you can see right there, and F of 2 happens to be 4. So you see there is more of a difference between the heights there. And you know, if you picked 1, one would be positive, 1 would be negative. Okay, we're still not done with this example because I want to kind of show you what the book does. So let me change over to purple pen. And you could actually ignore this, but I'm writing this because some of you might have looked at your book or looked at the solutions manual and say, well, what are they doing? This is looking weird. So basically, you've got a function f of x. And they say that function, they want you to find the linear approximation at the point A, or the x value A. So the y value is going to be f of A. So this is going to get a little theoretical. Some of you might want to close your eyes. So there's the point. And what also you can find is you can find the derivative and plug A into the derivative, and this gives you a slope. Now, I could use the y equals mx plus b, but I'm kind of feeling like maybe I'm going to use this. I'm going to use the point slope form. And the point slope form, it's been a while maybe since you've seen this. It's y minus y1 equals m times x minus x1. And this is the point slope form of a line. And here is the slope m, and the point is x1 comma y1. So I'm going to plug that point in this slope into this equation. It's going to get messy, you know, in terms of the symbols. And I did warn you that this was going to be a little theoretical. So you have y minus, the y value of the point is f of a equals m, which is f prime of a. Then we have x minus the x value of the point is a. I'm going to go ahead and add f of a to both sides. Y equals f of a plus f prime a all over x minus a. And then what your book does is they say, oh, guess what? This right here is L of x, which is f of a plus f prime of a times x minus a. Now, in some ways, if you're a math nerd, oh, well, that's really cool. We can pick up the tangent line by memorizing this formula here. And I think your book does that. But the deal is, I remember taking calculus, seeing this formula, this is what the teacher put up, and then hitting the test and completely freaking out on a problem like 1a because I didn't know that I was just finding the tangent line. And I believe that I even messed this up. I might have put a minus there or whatever. And so this is cute. And it also works. So I'm going to show you that it works on our example. On our example, we have a was 3. And so, you know, in our example, we could have gone like this. F of 3, I'm rewriting this, plus f prime of 3, x minus 3. And then, so I'm not going to go ahead and like move the papers around, but if you look at f of 3, that's 3 squared, which is 9. So I'm like looking at example 1, plus f prime of 3, and I believe we computed that to be 6, and then we have x minus 3. And so this is 9 plus 6x minus 18, and so this gives me 6x minus 9 is the linearization. And now let me go ahead and show you. That's exactly what we got for part A. So you may end up going to a tutor, or if you can find a tutor in these days, or you know, maybe online or whatever, and you would see that a lot of them will do the problem this purple way. You know, they'll say, oh yeah, here's the equation from the book, and we'll do this. And it almost feels like if you do like 5 of these problems like this, it doesn't even feel like you're finding the tangent line. You are, but you might feel like you're doing something different than what I did here. So, you know, you're the one to choose how to do the problems. I'm going to go ahead and do them the way I've been doing them initially without the purple pen. So that was problem 1. It took us a lot longer than it should have taken us, because I should have probably just stopped right there. But I wanted to give some insight on what is happening. So let's go ahead and do problem number 2. Okay, I'm not going to write the instructions again. What they want you to do is they want you to write the equation of the line that represents the linear approximation of the following function at the given point 1. Okay, and just like the other problem, part B, we'll use our linearization L to approximate that. Okay, so I know we can just in our calculator go square root of 1.1 and get the exact answer. We want the approximation. Okay, so what am I going to do with this problem? Let's do the thing that I did before. I want to go ahead and say, well, this is going to be the point. So I'm starting to do the problem now. So here's the problem. I have the point 1, comma, and how do I find the y-coordinate on the graph? I put that in there. F of 1 is the square root of 1, which is 1. Okay, so the point happens to be 1, 1. I want to find the slope. How do I find the slope? I have to take the derivative. So even if you were doing this the purple way, you would still have to take the derivative of that. So f of x is x to the 1/2. The derivative of that, I'll use the power rule, 1/2. And then we have x to the negative 1/2. And so the derivative is 1 over 2 root x. Okay. And you would still, if you were doing it the purple way, have to go f prime of this x value 1, which would be 1 over 2 times root 1, which is 1/2. So it has the slope of 1/2. So there's the slope, and there's a point. So what I'm going to do now is I'm going to go ahead and write out this equation, y equals mx plus b. I'm finding the tangent line at the point that has location 1. Y equals 1/2 x plus b. I have to figure out the value of b by plugging this point in here. So I get 1 equals 1/2 times 1 plus b. b also equals 1/2. So the linearization is going to be 1/2 x plus 1/2. So the answer to part A, I mean, I'm not going to put y equals, I'll put L of x equals 1/2 x plus 1/2. Okay, and there's the answer to part A. This gives me a linearization And I keep using the word linearization because I'm used to the Stewart calculus book. This gives me the linear approximation of f at 1. So that means this will do good for values that are close to 1 when you plug them into the function. And 1.1 is close to 1, so this should give me a pretty good approximation. So when I do that, for part B asks me to go L of 1.1. Okay, and you can do this on your calculator. What I ended up getting, or you can write this as 11 over 10 and write that out, combine the fractions. What I ended up getting is I ended up getting 1.05. And that happens to be the answer. And we're done with problem number 2. Okay, now for a few math nerd moments. So this is what you don't have to do. FYI, the actual value, when you put 1.1 into the function just being the square root of x, is the square root of 1.1, which you can do on your calculator, which gives you it's an irrational number, 0.4880888, and it just keeps going. Okay, so there's no pattern. Now, I would say that these two values are very close to each other. And in your homework and on the test, when they ask you to use the linear approximation to estimate the given quantity, if you put this down, that is incorrect. They want this approximation. So this essentially says that you can do square roots by hand. Not that you want to do square roots by hand, but you wonder how some computer programs work. Actually drawing in Word, Microsoft Word, and some other things will use linearizations or linear approximations. And in fact, in Calculus 2, when you study Taylor polynomials, it's completely related, and this is the jumping off point for finding Taylor polynomials, whatever that is. And the whole idea is you've got some nasty function, and I wouldn't say a square root of x is that nasty, but you could have a really nasty function, and you have to plug some x values in that are near a nice integer or whatever. L looks a lot better to do those calculations, and we talked about that. So that is problem number 2. And before we move on to the next problem, let's just take a look at the graph. Okay, so we have L of 1.1 and F of 1.1. L of 1.1 is right there, and F of 1.1 is right there. They almost like, because this can only do so many pixels when I graph this, it almost looks like the same, but it's a little different. It's just a little off, but you can see this linear approximation is good within a nice neighborhood of x equals 1. So you don't need to graph the graphs to do this. The graphs are kind of nice. If you're a math nerd, then, you know, use Desmos and you can take a look at graphs like this. Okay, what else do you do in your homework? In your homework, they ask you to do problems like this. It says, use linear approximations to estimate something like the cube root of 9. Okay, so there's a whole section of problems, you know, like 5 problems that were assigned or something that look like this in here. And, you know, maybe it might say the ln of something. And they go ahead and they put a number that's close to a number that you can actually take the cube root of. So remember, we can take the square root of 9 nicely in our heads, but the cube root of 9 is going to, we cannot do that in our heads. Unless you're a genius, and if you're a genius, you're probably, I mean, well, we don't want to talk to you, so let's do this here. So the thing they want you to do in these problems, I'm going to begin the problem, is they want you to figure out what f of x is. And f of x is going to be something that looks like this, and it's going to have an x in it instead. I'm going to say it's going to be the cube root of x. Okay, now I'm going to take an a value. Okay, so I'm going to go ahead and put a line there and say my work begins below the line, and I'm going to take an a value to be something that I can actually take the cube root of that's close to 9. I can take the cube root of 8. Okay, so what I'm trying to do is find the tangent line of this graph at x equals 8. So I'm going to need a point. The point's going to be 8, comma, and then how do I find the y value? I put 8 into the function f of 8, which is the cube root of 8, which is 2. Okay, so I have a point, and I need the slope. To get the slope, I have to take the derivative. To take the derivative, I'm going to write this to the 1/3 power. So f prime happens to be 1/3 x, and then I go 1/3 minus 1, this is negative 2/3. So this is f prime x equals 1 over 3 times x to the 2/3 power. So there's the derivative. And now what I'm going to do is I'm going to plug 8 into the derivative to find out what the slope is. So this problem, a lot of the problem is things that you have done in earlier sections where you're finding tangent lines. So this is going to be 1 over 3 times 8 to the 2/3. Order of operations says I must evaluate that exponent. To evaluate the exponent, I say the cube root of 8 is 2. 2 squared is 4. So this is 1 over 3 times 4, which is 1/12. This right here is the slope. So the next thing I'm going to do is I have a point and a slope. I'm going to write this down. Y equals mx plus b, and I know what the m is, it's 1/12. Y equals 1/12 x plus b. Okay, I'm going to bring it up here. I'm going to plug the x and y value into that equation, and I end up getting 2 equals 1/12 times 8 plus b. 2 equals 8/12, which is 2/3 plus b. You can either multiply everything in the equation by 3 or bring the 2/3 over. I don't know which one you want to do. I'll just go ahead and bring the 2/3 over. 2 minus 2/3 equals b, so that's 6/3 minus 2/3 is 4/3. This equals b. So I now know what b is, and of course I know what m is. I'm going to write the linear approximation, which is just the tangent line, and I'm using this fancy notation. 1/12 x plus 4/3. Okay, so the next thing I want to do is I want to go, because right here, this f of 9 is something that's very hard to do. I'm going to go L of 9 and get an approximation of the cube root of 9. And so I'm picking the 9 because I have that up there. So what does this give me? This gives me 9/12. 1/12 times 9, so this is 9/12 plus 4/3. I'll multiply and get a common denominator of 12, so it's going to be 16 plus 9. This is 25 over 12. That is the exact answer. If you put that in your calculator, you end up getting 2.083, and that's what it rounds to. But if you really wanted to know, it would actually be 3 repeating. So there is the approximation of the cube root of 9. We are done with the problem. FYI, if you actually wanted to know what f of 9 was, because that's going to be the exact value, you would put it into the function f, put 9 into that function, you'd get the cube root of 9, and you would do that on your calculator, you'd get 2.083 0, 0, 8, 3, 8, 2, and it would continue along, and your calculator would round it. And you can see that that is very close to our approximation. So we're doing things in calculus that, you know, we couldn't do without the calculus. And this is, once again, how some calculators and some computers work. They use linear approximations. Okay. So let us go ahead and talk about our next thing that we're going to do. The next thing we're going to do is something called differentials. Okay? So we just need a blank piece of paper. We're doing all right with the time, I guess. And what should we do? Let's take a look at our old function, which is the square root of x. I think this was our old one, and we had its derivative, which was 1 over 2 root x. And this guy right here, L of x, so this is an old problem that we did. The linear approximation at 1 is 1/2 x plus 1/2. And this was the linear approximation at x equals 1 or a equals 1. I'll just say at 1. And we also, you know, this is what we did. I think in our problem we approximated f of 1.1. What I'm going to do on this problem is I'm going to go ahead and compute L of 4. Now, is 4 really close to 1? And the answer is no. So I'm doing something, I'm using this linear approximation and I'm abusing it. I'm plugging something in that's not close to 1, and that's all right. So I'll end up getting 1/2 times 4, that's 2, plus 1/2, that's 2.5. And usually we use the improper fractions, but this time I'll go like that. Now I'm also going to go f of 4 because it's one that I can actually do without a calculator, and we put 4 in there, we get the square root of 4, which is 2. So those guys, I mean, even though they're close, maybe for government work they are, but they're not really close. Okay, they're not like super close. So what I'm going to do now is I'm going to show you the picture. And the picture looks like that. So f of 4 is 2. That was the last one I computed. And L of 4 was 2.5. So there's quite a difference there. So what am I going to do with this? What I'm going to do is I'm going to start at x equals 1. So here's the new part right here. You're like, well, where's the problems? And we'll do some problems after this development. Okay. Start at x equals 1. What is the change of height when you travel to x equals 4? Okay, so you know you can think of yourself as a little bug. You know, you're starting off at 1. You're starting off right here, 1, 1. What is the change of height when you travel from 1 to 4? Now, it all depends what you're traveling on. You could be traveling on the original curve, in which your change of height is 1. Or you could be traveling on the linear approximation, which the change of the height, how high did you go from here to here, this red point, would be 1.5. So basically, when I ask you the change of height, what is the change when you travel to x equals 4, and then, so part A would be on F, and then part B would be on L. Okay, so I'm going to leave a little space, and I could go back to the picture. We'll verify this with a picture, but when I travel on F, my change of height is really this. F 4 minus f of 1, which happens to be the displacement of the bug. So I don't know if we remember back to the bug. And so f of 4 is 2. This is the square root of 4 is 2. And f of 1 is 1. So the change of height when I travel from x equals 1 to x equals 4 on the graph of f is 1. And this is, we'll just say this is the change of height on f. Now when I travel on L, instead of going f of 4 minus f of 1, I'm going to go L of 4 minus L of 1. And so L of 4 happens to be, we already did that, it's 2.5. 2.5. And minus L of 1, 1/2 plus 1/2, that's 1. 2.5 minus 1 is 1.5. So this is the change of height on the linear approximation at 1. Okay, so now it's time for some notation here. And the notation happens to be this, dx, and we've seen that before when we had derivative notation. We'll see more of that. Dx and delta x. In the context of all these problems in this section, that's going to be equal. The dx and the delta x are equal, and what they happen to be is they happen to be the change in x. So you're going from x equals 1 to x equals 4. So the change in x is 4 minus 1. You're traveling 3, or maybe 3 seconds have gone by. So that is delta x or dx, and they are the same thing. You're like, well, why would you then have two different things? It's just the way it is, because we're going to have something different for y. And so this is the change of x. Okay, now this guy right up here, now our y's are changing, you know, that's because they say what is the change in the height, that's the change of y. These were different answers. So dy and delta y are not going to be the same. This one where you're actually doing the change of height on the original function, that is called delta y. Now when you are doing the change of the height on the linear approximation, that is called dy. And dx and dy are called differentials. Okay, so that's a definition. Differentials are dx and dy. dx is just the change of x, and dy is the change of y, but on the tangent line or on the linear approximation. Okay, looks like we're going to need more paper here. Let's continue to write things about this. Now, your homework problems, you're going to find that by the time I'm done explaining this, you'll understand what differentials are, hopefully, but the homework problems are not going to be that bad for this part here. So here's something to know, that when dx, or we can say, or that's delta x or dx, they're interchangeable. When that is tiny, then dy is going to be approximately delta y. Okay, so when like we went from 1 to 4, that wasn't tiny. And those guys are kind of close, but like if you were going from 1 to 1.1, then delta y and dy would be very close together. Okay. Now, here's the part that I want to warn you about. Your book, okay, so this is the book, then most books will do this. So let me write this in red, but maybe you don't want to look at this. I'm going to go ahead and write out this equation again. When they go like this, they say, oh, well, delta y, and they'll write out an equation for this. This is f of x plus delta x minus f of x. I mean, that's basically what this is, because my delta x in this is 3, so this is f of 1 plus 3 minus f of 1. So books will write that, and then they'll say, oh, dy is L of x plus delta x. And that could be a dx there too. And then we go minus L of x. So, you know what, I mean, that's cute, and it is true. But in terms of seeing this for the first time, maybe this was a bad thing to put here in this lecture. But I mean, I do this because some of you might be looking at the book and say, well, why is the book writing that? It is describing exactly what is happening here, where your starting value is 1 and your change of x is 3. And we saw that right there. Okay, now, here's the deal. In your homework, they're going to be asking you not to find delta y. And there are some calculus books that say find delta y and dy, but ours is just going to say find dy. And there is actually an easier way of finding dy than going L of 4 minus L of 1, because this would mean you would have to find the tangent line. And I'm not saying that that's difficult, but it's tedious. So there's a really fast way of finding dy. Let's go ahead and take a look at that. So dy, I'll write that down here. So dy has an easier formula. And here's the formula. Now I'll try to explain it. So dy equals f prime x times dx. So that's the formula. Wow. So that's crazy. And now let's think about our example. If the slope is 1/2, like it was, so we have our function of that's the linear approximation. The slope is 1/2, and you travel 3 feet on the x-axis. You're going to be going 1/2 when you travel 1 foot, and then the second foot you'll go another half up, and then the third foot you'll go another half foot up. You'll be going 1/2, which is the slope, times the distance you traveled, which is 3, or the change in the x, and that's what it is, the slope times the change in the x. And there's more complicated ways to explain this, but that's what you're doing. You know, so look at this. So look this picture here. We're traveling on the red line. You know, after 1 you went 1/2. If we're looking at the height, you've just gone up 1/2, and then you travel again, you've gone up 1/2, and then you travel again, you've gone up 1/2. You went 1/2 times 3 the distance traveled in terms of the x-axis. So that right there is an easier formula, and let's go ahead and take a look at this, and we'll look at some more pictures in terms of like what do the pictures mean on this. Some people want to see the pictures. So on ours, to find dy, we have f prime of x, which, you know, is out of range of the camera, but what it was 1/2 root x times dx. So for this function, that's what dy equals. And you know, up here you're going like, I thought dy equals 1/2. Well, let's go check this. This is dy equals 1/2 times the square root of the x value that I'm starting at was 1, and then dx happened to be 3. So we end up getting 3/2, or 1/2. And why is the easier formula sweeter? Because they might go ahead and ask you to find, you know, the change of y dy at other points that are far away from 1, and this will allow you to do that. Okay, so that's why this formula is the best formula. Best formula. Now, there is one other thing that we want to look at here. It is this. It's that when we learned about derivatives, we said the derivative can be written f prime of x. And then we said that another notation was dy dx. And lots of times we like to say, oh, do not treat that as a fraction. But when you're talking about differentials, it's all right to treat that as a fraction. And when I multiply both sides of this, we'll call it an equation because that's what it is, by dx, look what I end up getting. I end up getting our best formula for differentials. Because the dx is canceled, you get dy equals f prime x times dy. Okay, now let's take a look at the picture here. Not that they'll be asking you to draw the picture. The picture on this looks like this. Here's our change of x, which happens to be 3, delta x equals dx. And then in terms of the change in height on the graph of f, the original graph, that is called delta y. And the change of height on the linear approximation is called dy. Okay, and we try to approximate this by using something called, that we call dy. And if the change in x wasn't as great, like look over here, if the change of x was like 0.2, then it would look like the change in the heights for both of them are almost the same. And that's what we said I don't know where we said it. Yes, we said when delta x dx is tiny, then those guys are approximately equal. So this picture will be included with the PDFs on there, so you can take a look at the relationships there. Okay, the other thing that I wanted to do is before we moved on, the camera cut me off and I actually went a little further than I wanted to go. Let me actually just do this. Same example, we have x equals 1, delta x equals 0.2. So let's find delta y and dy. Okay, delta y, remember my original function was f of x equals the square root of x. So delta y is going to be f of 1.2, because that is where you're going to. You have 1, and then we add that. And then we have minus f of 1. And so when you do that on your calculator, you end up getting 0.09544551, etc. Okay, and your calculator is going to round. Now dy, which is 1 over 2 root x, that's the derivative, times dx, and we have that written down above. Let's go ahead and put x equals 1 in there. So I have 1 over 2 times the square root of 1, and then we have dx is 0.2 in this example. So that's like 1/5 times 1/2, which is 1/10 or 0.1. And so that is what dy is. And I know we can go back to this picture. Let me go back to this picture here, and we can see, at 0.2, where are we at? 1.2, so when we change from 1 to 1.2, when you change on the graph of f and change on the graph of L, it looks like the change of the height is very close, and it is. And so I think what we should do now is get to some of the homework problems that you will see. Because, I mean, what do you have to know how to do in your homework? And it's probably not going to be, as involved as that. I told you what delta y and dy was, but I don't think they ask you for delta y in your homework. It's good to know because in Calculus 3, you're going to see a dz and a delta z, and it means kind of the same thing, except you're doing things in 3 dimensions. So problem number 4 says find dy. So this right here, what you want to do is you want to say, well, dy is, I'm going to take the derivative of this. So this is the chain rule. We have 3e to the 3x, and then we have dx. There's your answer. Let's do problem number 5. That's as simple as it gets. And problem number 5 says find dy Now notice it's not saying dy over dx, which would just then be the derivative. It's just saying dy. Well, this equals the derivative of ln something is 1 over the something, and then the chain rule, we do the derivative of the something. So you're going to end up getting 2 over 2x minus 1, okay, so there's that, times dx. So that's what they ask you to do in your homework. And let's recap, because it was pretty complicated and I had pictures and all that stuff. The recap. In your homework, they're going to ask you to find a linear approximation of a function at a. So what do? You find the tangent line at a and then replace y with L of x. So the linear approximation of f at a is just the tangent line. The other part of your homework is going to ask you to find the differential of f. We just did 2 problems. It's pretty straightforward. You go dy. That's not a minus. I guess I was just saying. Let me just put arrows here. Oh, great. Making this worse. So I don't know what those are, by the way. They look like arrows. So dy is the derivative times dx, which we had done here, which really is not going to take that long because you're just taking a derivative and you are getting used to this new notation. Let's go ahead and do, it's problem number 58 in the homework problems. I'm going to title this number 6. And you get 3 problems like this at the homework. I would do these 3 problems last. Maybe it kind of shows you where people use differentials in the real world. Sometimes you're expanding metal or you're doing something that has just a tiny change and you want to approximate like when the radius increases from something to something. So let's go ahead and do this. It says approximate the change in volume of a right circular cone. Right circular cone looks like this. Now, they could not be a right circular cone, and they could be at a slant, and so you can have weird kind of cones, but it's kind of like an ice cream cone. And there's a circle at the bottom. Approximate the change in the volume of a right circular cone of fixed height, h equals 4. So I'm going to put that right here, h equals 4 meters, so I don't lose it. When its radius increases, so radius increases from 3 meters to 3.05 meters. So we actually have a dr, now it's not x, now it's r. Look, r is playing the role of x and v is playing the role of y. dr equals the change that I have, which is actually 0.05, which is 5 over 100, which is 1 over 20. Okay, so you can write it in any of those ways. Now, in your homework, be careful, because on some of these problems, they might say it changes from 3 meters to 2.99, in which dr, and we never said this until now, but dr is the change of height. Sometimes it could be negative. So be prepared for your homework. If it's negative, it's not going to be a big deal. You put a negative there, and then you'll plug it into the formula. Okay, so now we come over to this formula, which is given. It's not like you're going to have to remember all these formulas from geometry. And you want to approximate the change in the volume. So approximating the change in the volume, we're going to use dV. The actual change of the volume would be delta V. So this is the approximate. We're using a tangent line to do this. And this is the whole differential thing. So this is going to be V prime of R dr. I know this is freaky because we're used to x is there and, y is there and x is there, but we're doing things a little differently now. And now I'm going to take the derivative with respect to r. H is, what did it say about h? H is fixed, so it's not changing on this one. So we're going to treat h as a constant. So when I go to do this, dv equals, I'm taking the derivative with respect to r is the only variable there, and it's going to be 2r. So really, we'll write this as 2/3 pi r h, and then over here we have to write dr. Let's go ahead and plug some values in. dv equals 2/3 pi, h is 4, and dr is 1 over 20. Okay, so actually, I forgot r. How embarrassing. Do I have my, oh yeah, here it is. So I wasn't being very careful. I have 2/3 pi. There was an r that I did not put in there. So let's go ahead and clean things up. Come on. Okay, there it is. So 2 pi r, that r was, okay, so that's going to be 3. Nice. And then h is 4. Okay, good. Just notice that r. Okay, so now that's kind of what I wanted to see. So the 3's are going to cancel. And then we have the 20 and the 4. They're also going to cancel. Let's see, that's going to become 1/5. So this will become 1/5. And wow, so what do we end up getting? We end up getting dv equals 2 pi, everything's gone, 2 pi over 5. 2 pi over 5. And really what it is the change in the volume, so that's cubic meters. And so when you look at the answers in the back, they're going to say delta V. Now does this equal delta V? No, this is just the approximation using a tangent line. So delta V is approximately equal to the same thing. 2 pi over 5 cubic meters. And so, you know, when you look at your answers in the back of the book, they'll have them written like that. So that is the deal. That completes this problem. You know, if you really want it to, this is just kind of a reminder of we have these two things, dv and delta v. And some of you can just ignore what I'm writing now. dv is the linearization at r equals 3, evaluated at 3.05 minus L of 3. That will give you exactly this. Now, of course, we said this was not as good of a way. The best way is to actually just do the differentials right there. And this here is a differential. Delta V is actually the original function, which is not called f, it's called v. So it's going to be v of 3.05 minus v of 3. And you'd have to put h equals 4 in there to do that. And I bet if you did this right here, which they didn't ask for, it would be very close to this. And how would you see this? You would actually just multiply this out on your calculator. I think on this one you end up getting like 1.257, I think it was meters. It's all meters cubed. And then this guy right here, I don't think he'd be 1.257, but he would be very close. And this is the actual change. So, maybe that confused you, but in your homework you'll have 3 problems like this. And once again, reminding you sometimes the dr or the dx or whatever it is, it could sometimes be negative because the change in the height, you could actually be going down. The displacement can be negative. So that completes this section, section 4.6. You guys have a good day.